Hello everyone, welcome back to this channel. And in the past few videos, we have learned about what is force and how to quantify them. And in the chapter 4 alone, we learned how forces can be used to create a turning effect. And in this chapter, we're going to look into how forces will affect matters. So these are 4 subtopics that we'll go into in a while. And let's look into the first one, forces acting on solids. It's important to understand this topic, especially for engineers, because every material out there, they behave differently when forces are applied on them. And therefore, the engineers here needs to understand the behavior of each material so that we know which materials to use for an application, great? So this is how forces can change the size and shape of an object. For instance, we have a rubber band here. So if you were to um, stretch it, you will get a different size and also probably a different shape. And can also squash a border like that. Can bend an object. We can twist it. So there are lots of ways we can apply force on solids, and different materials will behave differently when forces are applied on them. Some materials, like rubber band, will return to its original shape once the external force is removed. But then some other materials like metal or gold, they do not return to the original shape. They are called permanently deformed. So let's look into specifically one type of solid here called springs. And springs are designed to stretch a long way when a force is applied. So it's easy to measure how their length changes. And that could help us to derive some relationship between the forces applied and also the amount of extension. So here is an experiment that physics students do to measure basically how, when we apply force on the spring, how much does it extend? So here are two different terms. First is the amount of load you put on the spring. So that represents the force that is acting on the spring. Whereas the extension is the increased length of an object. How much does it increase when an object is placed on them? So let's do a work example to show you how this experiment could potentially create a conclusion. Here, let's say when we start with load 0 Newton, that means we don't put anything in. I'm going to have no extension. All right. So the extension here should be 0, meaning the length is the original length. And as I increase the load to 1 Newton, the length of the string becomes 17.5, meaning now the extension is 17.5 minus 15, you got 2.5. And followed by 2 Newton, our extension will be 5 Newton, 5 cm, 7.5, 10, and look what's happening in load 5 Newton and 6 Newton. Now, the extension, instead of 12.5, it is actually 20. Because the original length is 15 and the extended spring is 35, so we got 20, and followed by 30. Something different is happening here, but we'll discuss in a while. So that's what we'll get after we populate the extension column. The question asks, when the load is increasing from 0 Newton to 4 Newton, how does the extension of the spring change? And we can see from here to here, the extension of the spring actually increases linearly, meaning the increase is constant. Every 1 Newton of force you add, 2.5 extension is added, right? So, in other words, doubling the load doubles the extension, which is correct. But in the next question here, do you observe the same pattern when the load is increased to 5 Newton to 6 Newton? Why is that so? And no, because instead of increasing the extension by 2.5, now an additional 1 Newton of load would increase it by 10 Newton. And this happens because now we say the spring has become permanently damaged. So we all have the experience when we just stretch our string and it just wouldn't return to its original shape because it's permanently deformed. And that's what's happening here. And that will lead to one of the important stuff we'll learn later, but just bear with me. And the other things you need to learn in this spring chapter is how to draw a graph for the load and also the extension. All right, I should label it here, extension. So meaning we need to plot our result on a graph. So I'm going to show you how to do that. Our first column, we have 0. So the extension is also 0, meaning there's a point here. And followed by 1 Newton and 2.5 extension. It will be another point here. And followed by here, here, here. And when the load is 5 Newton, you can see that the extension is now 20. So I'm going to move my point to 520. It's not very perfect, but it does the job. Okay. So if I were to draw, connect all the dots here, this is what I will be getting. Again, it's not very perfect because I don't have a ruler. And that's what you get for the extension of the spring when load is applied to it. And this is called a load extension graph, meaning as the load increases, the extension also increases. But until a certain point, the extension just go way beyond the predicted route. All right. So let's look into the third subtopic, which is called Hooke's law. That basically explains how spring reacts in this way. So let's look into what it is. And one reason we learn about spring in this video, just for you to keep you engaged, is that a lot of the materials out there, they use the springs. For instance, your mattress, the suspension in your car, and also door hinges. And by understanding Hooke's law, which we'll talk about later, we'll learn how springs react when force is applied on them. Remember, this chapter is about forces and matter, and we'll learn how forces can change the state of the matter. And by understanding how they react, we can use this spring effectively in a lot of applications. So this is our graph just now. As you increase the force, you get the extension and up to a point. So at first, the graph is a straight line, meaning from here to here. And this shows that the extension is proportional to the load. Proportional means when the load increases, the extension also increases in the same pattern. But at a certain point, the graph starts curving and the line slopes up less steeply. This point is called the limit of proportionality. So up until this limit, the extension of the spring is proportional. So this is the point. We call it the point which the spring started to get permanently deformed, right? The limit of proportionality. So up until this point, the graph is still linear, but after that, it no longer be linear. And beyond the limit of proportionality, this part of the graph here, the extension is no longer proportional. The string is called permanently deformed. We can't make it return to original shape. And this is actually discovered by Robert Hooke, and he discovered this law called Hooke's law. The law states that the extension of a spring is proportional to the load, meaning the more load we add, the more extension we're gonna get, provided the limit of proportionality is not exceeded, meaning up until this point, this will show you the Hooke's law. And for Hooke's law, we have an equation here, which is force equal to K times X, which K is the spring constant, X is the extension. And if you look into the graph of it, a spring that has high K is probably going to look like this. And a spring that has lower K, which will look like that. So in other words, if you learn gradient in mathematics, you can also see K as the gradient. But what exactly is this spring constant thingy, right? It's basically is the stiffness, it represents the stiffness of the spring. So if we look into two different springs here, let's say this spring has a high spring constant, and it means there's less extension per unit force. In other words, it's very stiff that it can't just make it extend very much. And the graph of it will look like this. The K is very high, therefore it has a high gradient. Whereas spring with low spring constant, it works like that. It's a little bit less stiff, easy to create an extension. Therefore, if you look into the graph here, the more force you added, the more extension you get as compared to the one with high spring constant. So that's the intuition of what spring constant is. And let's look into some of the exercises. A spring has a spring constant K of 20 Newton cm. What load is needed to produce an extension of 2.5? And if we look into our formula, F equal to Kx, and the quantity we need to find is F. What force do we need? Given that the spring constant is 20, so I'll just sub in the value, extension is 2.5. And here I get 20 times 2.5, which is 50 Newton. Great. So that's how we can solve our problem here. Let's move on. A spring requires another work example, a load of 7.5 Newton to increase its length by 5 cm. What load will give it an extension of 12 cm? So this is actually a two-part question. So first part, increase the length. We got, again, the equation F equal to Kx. What we lack here is the spring constant. We have the load, which is 7.5, equal to K, and the extension is 5. So therefore, my K will be equal to 3 over 2 Newton slash cm. So that's the unit for spring constant. And B, let's solve. Now we know what the spring constant is. We can use the same formula, but now we need to find F. So I'm going to sub in the K that I found into the formula. 3 over 2 times 12, I got 18 Newton. So if we look into the answer, that's all about it. All right, so let's move on into pressure. And for the first three subtopics here, we basically learn how forces can create an effect on a solid. So now we're going to look into how forces actually relates to pressure. I mean, not the one you get when you're studying. So the pressure that we have here, the first one is underwater. Imagine this submarine is under the sea here. So there's pressure exerted on it, which is from the water, because the water is pressing the submarine. So the submarine here experiences pressure. Whereas the other type of pressure is the one that we experiences now on Earth. We don't really feel it because internally we still have the pressure inwards. So therefore, and the pressure we experience on Earth is called the atmospheric pressure, and it's caused by the air particles. And the air particles is actually hitting us all the time. We just don't feel like it. All right. And to compare the pressure on in the water and also in air is that the pressure in the water will have greater effect. Greater effect. This is because if you remember kinetic particles of model, the particles in water is more closely packed, and therefore when they hit you, you're gonna experience higher pressure as compared to getting hit by the air particles. So what is pressure, right? Pressure is actually caused by the collision of molecule with every surface they collide with. So for pressure, the first formula that will be learned is called pressure equal to F divided by A. And to show you what this formula means is that just imagine this, you are this guy, and then you try to step on two different objects. The first one is the ball, and the other one is the nail. And you will feel a lot more painful when you step on the nail. And this is because the nail exerts more pressure on you when you step on it. And the reason why this will give you more pressure is because its area of contact is very, very small. So just imagine, I'm going to show you in this equation here, work example, which exerts a greater pressure. A force on 200 Newton, let's say 200 Newton is a shoe here, on 1 meter square, or the same force acting on 2 meters square. And by using the formula, we can determine which one actually has more pressure. So P equal to F over AE. My force is 200, and the first area is 1 meter. So I'm going to get 200, the unit for pressure, Pascal. So that's the first one. And if we were to change the area into 2 meter square, so I'm going to get 200 divided by 2. And see, I'll get 100 Pascal instead. So you can see that when the area of contact here is very, very small, this will result in the pressure being very large. And this is why, because the area of contact of the nail is very, very small. This will result in very high pressure that makes you super painful when you step on it. But do not try it at home. So that's basically the solution. A force acting on a smaller area will have greater pressure. Second one, what pressure is exerted by a force of 50,000 Newton acting on 2.5 Newton. So again, I'm just going to use the formula 50,000 Newton divided by area 2.5 meters square, which I will get 2,500 Pascal. Alright, sorry, should be 2,000 Pascal. So if I look into it, yeah, 20,000, my bad. I don't have my calculator here, but the answer is 20,000 Pascal. And that's pressure, the first type of pressure we'll learn in this chapter. The second type of pressure you'll learn, as mentioned, is how we measure the pressure on an object underwater. We have two submarines here, and the intuition is that the deeper one object dives into the water, the greater the pressure. So meaning the second submarine here will experience higher pressure. And using this intuition, we know that pressure under liquid depends on two things: the density of the water and also the depth of it from the water surface. And here's the equation to calculate pressure underwater. Remember, it's different as compared to the first pressure formula we learned. So this is used when we want to measure pressure underwater, liquid. We use the density of the liquid multiplied by the gravitational field strength multiplied by the height. We call it PGH. Let's solve some problem here. Calculate the pressure at the bottom of swimming pool that is in 2.5 meters deep. And how does it compare to the atmospheric pressure, which is 100,000 Pascal, using the fact that density is 1,000. So the formula, pressure equal to rho GH. This is called rho and physics term. Density is 1,000. Gravitational forces, let's assume that for 10 to make calculation easier. Height is the depth of it, which is 2.5. So we got 10,000 multiplied by 2.5, which is 25,000. No. All right, so let's look into it. I have an arrow here. So 225,000 Pascal. If you compare it with the atmospheric pressure, you see that it's actually way less than the numbers that the value of the atmospheric pressure. So that's one work example. So now let's look into some past year question. All right. By the way, I forgot to show this. If you were to use 9.8 here, you should have gotten instead of 245,000, it should be 24.5 thousand. All right. So at the swimming pool is smaller. This is when you do an true or false question. It's smaller than the atmospheric pressure. Great. So let's look into some of the past year question. A small metal block is suspended under the surface of a beaker of water by a string. The metal block experiences the pressure exerted by liquid. To show you how it works, so this is basically the liquid, the pressure of the liquid acting on the object. They are saying what would increase the pressure exerted on a metal block. So to solve this question, we need to recap the formulas that we learned. Pressure under liquid is rho GH. So let's look into each example to make sure to check whether they are reasonable. Increase the surface area of the stone. If we look into this formula, surface area doesn't matter, so I'm not going to choose this. Using a liquid with lower density. If you were to decrease the density, the pressure would decrease. So that's not what we want because we want to increase the pressure, right? And that's second one would be incorrect. Increase the mass. We don't have mass in our formula, so that's another one. Lowering the metal block deeper into the liquid. And when we do that, we are basically increasing the H. So that's actually the answer. When we increase the H, we'll get a higher pressure. So the answer is donkey. So let's move on. On which surface should the block be laid to produce the larger pressure? And because now we are dealing with pressure not under liquid but an object here, so I'm going to use the outer formula, F over A. And we know that we will have larger pressure when the area is very low. So to know whether to choose A, B, C, or D, we just need to find the surface which has the lowest area. Without calculating anything, I know that C actually has the lowest area, meaning it's gonna give me the highest pressure. So my answer here is C. And here we have it. Next question. 3 beakers of water are placed on the table. The depth of water is the same. In which container does the water exert the greatest pressure? Alright, so now we have pressure under liquid, so it's rho GH, and it depends on density. And since since 3 beakers contain the same liquid water, the density will be the same. Gravitational force is the same as well because they are on Earth, they're placed on Earth. And therefore, the only thing that will affect the pressure is the depth. But if you look into this dotted line here, if we look into the bottom of the glass, they actually have the same height. And therefore, the answer is D here. The pressure is the same in all three because the depth of the water in 3 beakers are the same. So my answer is D, none, because the pressure is the same in all three. So let's look into this last question here. The diagram shows a submarine, and the submarine is fully submerged in the sea. The density, let's underline the keyword, is 1020. Atmospheric pressure is 1000 kilopascal. And total pressure on the top surface of the submarine is 500 kilopascal. Calculate the depth of the top surface of the submarine below the surface of the sea. So I just draw a random wave here to show you where's the sea. And they're basically saying that the atmospheric pressure here, pressure exerted by the air is 1000 kilopascal. And the total pressure here is 500 kilopascal. So to solve this question, we know that we need to use the formula PGH, rho GH, to find the height of it. But what will be our pressure here? So the total pressure underwater is 500, but then 100 of them is exerted by the air, the atmospheric pressure. So we know that for PGH, the total pressure should be 400 kilopascal, 400,000 kilopascal, equal to rho 1020. I'm going to use 10. Right, maybe in your new syllabus, let's use 9.8. And H is the amount that we need to find. And the reason I'm using 400,000 Pascal here is because 100 of it is from the atmospheric, so we don't count that. So I'm going to use 500K minus 100K to get 400K. And if I were to plug everything into the equation, so this is how I will solve it, 9.8. And if I plug that all in, you should get 39 meter. You get a slightly different answer because in the new Cambridge syllabus, they require you to use 9.8 instead of 10 for your gravitational acceleration. So that's something you need to take note of. But that's basically how you solve it. And that's about it for this chapter. So in this chapter, we learned how forces will affect spring. We learned about Hooke's law and what is the limit of proportionality. And also learned the two formulas to calculate pressure. The first one, pressure under liquid, we got rho GH. And also pressure, normal pressure, we got pressure equal to force divided by area. And that's about it. Thank you for watching, and I'll see you in the next video.